In this video, we will look at the different techniques used to graph rational functions. As a reminder, a rational function is one that is set up as two different polynomials, one in the numerator, one in the denominator. An example of a rational function would be something like this, where we have two different polynomials, and we'll look at all the different options depending on what the degree of the numerator is versus what the degree of the denominator is. So here's a formal definition where p of x would be the name of one polynomial and q of x would be the name of another polynomial. And we have to make sure that the denominator in the polynomial in the denominator doesn't equal 0. And so when we look at this example here, we can see that 5 is a number that we cannot have in the domain. And then looking at the graph here on the right, we can see that that makes sense based on what the graph looks like. This blue line that's drawn, the dotted line, we call that an asymptote. And it's not really part of the graph, it's just meant as to show you that that's the number that's been removed from the domain. So again, this is called an asymptote. And it's usually given an equation of a line, which in this case, the asymptote would be the line x equals 5, right? So that's matching up with that point removed from the domain. In general, let's talk about what the graph of 1 over x looks like. So the graph of 1 over x is split up because if we have 1 over x, we can't have 0 being included as part of the graph. So it actually looks like this. And then the other part of the graph is here. Let's talk about why. When I choose a really large number to plug in for x, let's say I look at f of 1,000. That's going to be 1 over 1,000, or 0.001, right? So that's a really small number. And we can see on that part of the graph that this is getting really close to the x-axis. The x-axis is acting as an asymptote in this case. It's not going to cross the x-axis, but it gets really, really close to, because the numbers get smaller and smaller as we plug in higher values of x. On the other part of the graph, if I plug in a number that's very close to 0, but just on the right side, on the positive side, let's say I plug in f of 1 over 1,000. When I put that into the fraction, we're going to flip the fraction upside down and I end up with 1,000. So that's why as I get closer to the x-axis, the numbers are getting really, really large. I'm sorry, the y-axis. The y-axis also acts as an asymptote. And then on this other part of the graph in quadrant 3, it's got following the same idea, it's just upside down because we're talking about negative numbers, right? So we can think about this original graph that we were talking about as a graph transformation from 1 over x. What we've done is we've plugged -5 into the original. If I think about this as the original graph, this other one would be f of x minus 5. And so we have a shift to the right by 5 units, right? And that's kind of reflected in the graph that we're seeing. All right, here's a couple different examples. Here's the example of 1 over x that I was just talking about. But then when we look at 1 over x squared, that squared is going to make every number that you plug in a positive number. And so that other side of the graph is reflected up into the positive realm. So again, depending on what the degree is and what the different components are, these graphs look very different, but know that they're all sort of disjoint and have different pieces among them. looking at these two functions, they're asking us to just determine what the domain is. And you can see these might be pictures that you could get if you plugged this function into Desmos. But Desmos isn't going to tell you what the asymptotes are. And so you've got to determine that on your own. Looking down below, we can see that the numbers -2 and 1 have been removed from the domain in this first function. And that shouldn't be surprising because if we look at the denominator, it factors into x plus 2, x minus 1. And so the -2 and the 1 have been removed because those are points that will cause the denominator to be 0. Similarly, for the second one, this factors into 2 times x minus 3. So 3 has been removed from the domain. So what we're going to be heading towards is this idea that the asymptote is going to come from what the zeros of the domain are. So if I go to 3 here, that's where my asymptote is going to sit. And then over in the first one at -2, I've got an asymptote, and then also at 1. That kind of matches up with the graph, right? Here are 2 more examples. Now, this graph E had sort of a similar denominator. I think that factors a little bit differently, right? Because it would be x minus 2 and x plus 1 instead. So we can see that we still have those 2 asymptotes, one at +2 and one at -1. But we've also got this additional piece of the graph that's happening, right? It sort of looks different. This one has this sort of what looks like a cubic in the middle, whereas this other one had what looked like a quadratic in the middle, right? And that's based on what's happening with the degree of the numerator and the denominator. This other one over here, there's a special case when the degree of the top and the bottom is exactly the same, we get what's called a slant asymptote. So we can see that for the denominator, x cannot be equal to -1. And so we do have one asymptote that's sitting at -1. Try to draw it as best I can in here. But then there's also another asymptote that's going in a diagonal fashion. And we'll talk about how we find what that equation is. So I mentioned this already. The vertical asymptotes are going to come from the zeros of the denominator. So the first thing that you'll want to do is factor the denominator of a rational function and then determine where those asymptotes are going to be. In this case, we're at x equals -4 and x equals 2. Here's another example where we factor the denominator. We factored the numerator too because we're going to use that for a different part of graphing. The denominator you can see factored like this. So we have asymptotes at x equals 1 and x equals -1. Now, one of the interesting things about this particular graph is that the term x, these two canceled each other. And so technically there would have been an asymptote also at x equals 0 because that's a number that we can't plug into the original function. But that factor canceled. But because it's part of the original function that we started with, we have a hole rather than an asymptote in the graph at that point. The graph is still undefined at that point. Now, how did we determine that it was at 0, 4? If you plug 0 into the original, you'll get 4 as the output. So f of 0 would be 0 squared minus 4 times 0. I just paused there for a second because what I was saying was not correct. What we need to do is go back to this version and write it simplified, right? Because I was going to end up getting 0 there. f of x, the modified version will be x minus 4 over x plus 1, x minus 1. Now plug in 0. And I'll get negative 4 over 1 and negative 1. So I'm getting 4 as the output value. So again, don't plug it into this version. Don't plug into the original version, because that's going to end up equaling 0. I've got 0 over 0. You have to plug into the version where you've simplified the polynomial to figure out what the output value is. This is the formal definition of asymptotes, but then there is behavior that happens as we move towards the asymptotes, right? In the example that we just had before, as the graph is approaching the asymptote x equals negative 1, this one here, I have two different things happening. As I approach the asymptote from the right-hand side, it looks like the y values are going up to positive infinity. But as I approach the asymptote from the left-hand side, the y values are going down towards negative infinity. We'll talk about in some examples of graphing how we determine what direction the graph is moving. This slide is talking about horizontal asymptotes. Horizontal asymptotes happen at in different possibilities. This first example is one where the degree of the top and the bottom are identical. They're both to the 4th power in this case. And the horizontal asymptote ends up being a combination of just the first two terms. Let's talk about why that is. If I were to take every single term in this original function here and divide it by x to the 4th power, this would be 10 over x squared plus 1 over x to the 4th. I'm just rewriting all of these items. This would be 1. So what I've done is I've taken all of the terms in the original and I divided each of them by x to the 4th power, because that's the highest power that I have in both numerator and denominator. When I plug in really, really large values of x, all of these fractions are going to go to 0. We saw that when we were looking at the graph of 1 over x. When you plug really, really large numbers into the denominator, the whole fraction gets close to 0. So when I plug in values at the extremes, really out far towards positive infinity or towards negative infinity, the only two values that really end up mattering that stay are these two. And so when we're talking about a horizontal asymptote, we're just looking at the leading coefficient of both the numerator and the denominator. And so the equation of this line here is y equals negative 7 over 11. That's this line right here. That's the horizontal asymptote that we have. Here's an example of the degree being the same. So I look at the coefficient in front of both of them. So the horizontal asymptote is 2 over 1. And you can see that I've got that drawn here. And then because the denominator cannot have 0 plugged in, we have a vertical asymptote at x equals 0. In this case, we could have plugged in a couple test values to see what's happening with the rest of the graph. But another idea would be to just plug in values very close on the left and right of the vertical asymptote. Like let's say I plugged in f of 0.1, a point that's just to the right of the y-axis in this case. Or I plug in f of negative 0.1, just to the left. If I plug those in and I see what the output values are, that will tell me that because everything is squared, I'm going to end up getting a positive output value. And here I'll also end up getting a positive output value. Because those are positive, that tells me that the graph is moving up, and then I know that this is what's happening with this part of the graph. And then over here, it's going to approach this horizontal asymptote. So I can plug in other points if I want, just grabbing a couple points to kind of get a structure for the graph, but you'll be using Desmos for most of your graphing, and what I'll want you to describe is how to find what the asymptotes are. So there are three different options for the asymptote. The first is the one we just talked about, is that when the numerator and the denominator have the same degree, and we're looking at the leading coefficients, right? And we set up this fraction. When the degree of the numerator is less than the degree of the denominator, like x plus 2 over x squared minus 7x plus 10, something like this. In this particular case, the horizontal asymptote will be at y equals 0, or the x-axis. And that's because this is ultimately going to be a graph transformation of 1 over x, right? Where the degree of the top is less than the degree of the bottom. Now, when the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote. So if I had it in the reverse, if I had x squared minus 7x plus 10 over x plus 2, then there would be no horizontal asymptote. That's because what we could do is we could actually divide this out and we could get a different polynomial, right? We could use long division there. And in these cases where there's potentially a slant asymptote, then we will have to do long division. This happens when the degree of the numerator is exactly 1 more than the degree of the denominator. So an example would be x cubed plus 2x minus 8 over x squared plus 7x minus 10, right? When the degree of the numerator is exactly 1 more, then there's potentially a slant asymptote. A couple key things to keep is that a rational function is never going to pass a vertical asymptote, but it may cross a horizontal asymptote just based on the different components of a graph. There may be that the graph is acting like a horizontal asymptote for parts of the graph, but not for another section of it. What I mean by that is we could have a horizontal asymptote like this, and we could have this part of the graph. It's acting as an asymptote for these two parts of the graph, right? But then we have this other piece sort of in the middle that it crosses. So it can be that it acts as an asymptote just for parts of the graph. All right, so here's how we find a slant asymptote. Again, the degree of the top is exactly 1 more than the degree of the bottom, and so we do division here. And it does turn out that we can, in this particular case, do synthetic division, but a lot of times we can't. So typically in this case, we would do long division. So I'll do long division here. We want to know how many times what we need to multiply x by to get to 2x squared, which would be 2x. So we'll match up the degree and write it in that column. And then we multiply down. So we'll have 2x squared minus 4x. We subtract both of these items. So then this changes to a positive x minus 1. So I'll put a plus 1 here. And then when I multiply, I get x minus 2. Subtract both items, and I end up with 1 as a remainder. So rewriting this original function. A different way that I can write it is this. 2x plus 1, that's the quotient that I got, plus the remainder over the divisor, right? We talked about this last week, that this is a different way of writing the original function. It turns out that this part of the function is the slant asymptote. So this line that's been graphed is y equals 2x plus 1. The y-intercept is 1, I can see that here, and then the slope is equal to 2, right? So they graph that. They also have an asymptote at x equals 2 because of the denominator. We see that here. And then plugging in a couple points to figure out where the graph sits, we can get this picture of the graph. So here are the formal steps to graphing a rational function. We are going to find the zeros of the denominator to get the asymptotes, the vertical asymptotes. We will use the different options based on the degrees of the numerator and denominator to determine whether there is a horizontal or an oblique asymptote. We'll find the zeros, or the x-intercepts, and these come from the zeros of the numerator. A function is not going to have the denominator ever equal 0. We're removing those points. So when we want to know when the function equals 0, what its x-intercepts are, we're only going to look at the numerator. So the x-intercepts will come from the zeros of the numerator. And then to get the y-intercept, of course, we plug 0 in for x. And then if we need to, we plug in a couple additional points just into the function to see if we can get a general idea of what the graph looks like. But again, for number 5, you'll more than likely just use Desmos. All right, let's go through a full example here. I have a picture of the graph sitting here because, again, you'll be able to just plug this function into Desmos and get a picture, but we have to supply all of the algebra behind to justify what the graph looks like. So let's start with number 1, which is finding the vertical asymptotes. And they come from the zeros of the denominator. So if we factor this, let's see, we would have 3x minus 2 and x plus 3. I did this ahead of time. And then, so that means that the asymptotes are going to be at x equals 2/3, right? And x equals -3. Again, I'm looking for the zeros of the denominator, or the points that need to be removed from the domain. I can see both of those asymptotes reflected here in the graph. The second step is to find any horizontal asymptotes if they exist. The degree of the numerator is less than the degree of the denominator. And that was one of the options we had in the slide above, which says that the horizontal asymptote is going to be at the x-axis, or at y equals 0. And this is kind of following that idea I was talking about just a minute ago. There is an asymptote here at the x-axis, and it's acting on this part of the graph on the right and this part of the graph on the left. But we can see that that portion in the middle is actually crossing that particular asymptote, the horizontal one. All right, part 3 is to find the x-intercepts, or the zeros. So part 3, to find the zeros. And again, those are zeros of the numerator. So the numerator is 2x plus 3. So we'll have x equals negative 3 halves. So negative 3 halves, comma 0 is our x-intercept. And that's reflected right here. And then we'll find the y-intercept by plugging in 0 to the original. So again, 2x plus 3, 2 times 0 plus 3, over 3x squared plus 7x, 3x squared plus 7x, is it plus 3? Minus 6. So I'm getting 3 over negative 6, which is negative 1/2. So the y-intercept is at 0, negative 1/2. And looking back up at the graph, I can see that that's reflected right here. So what you'll be turning in for me is a picture of the Desmos graph where you have this plugged in, and that'll give you just the red parts of the graph. But then what you're going to do is give me the justification for how you found the x and y intercept. You can click on the graph and it'll show you, but you need to show me the math, and then also what the equations of the asymptotes are. And the other thing that we probably want to talk about is how do we determine what's happening near the asymptotes? Because if I were doing this by hand, what I would have had at this point is two asymptotes, one at negative 3. Let's just go 1, 2, 3, like this, right? I would have had an asymptote here, and then the other one was at, I think it was at 2/3. So like about here. I would have that. And then I also had the x-axis as an asymptote, right? And then I would have had two intercepts. One was at negative 3 halves here, and the other was at negative 1/2. So about here, right? This is all that I would have had. And I need to figure out what's happening with the rest of the graph. So what we do is we look at the behavior as we get close to the asymptotes. And to do this, I'm going to look at the factored version of the equation. So I'll write that over here. Our original equation is 2x plus 3 over 3x minus 2 and x plus 3. Okay. Now I'm going to plug in points just to the left and the right of this asymptote right here. So that one was at negative 3. So I'm going to plug in, let's say, negative 3.1 and negative 2.9. Those are points that are just to the left and to the right of that asymptote. X equals negative 3. And what I'm going to do is I'm going to look at the original, and all I want to know is whether I'm getting something positive or if I'm getting something negative. When I plug negative 2.3 into that factored version, the factor on the top is going to I'm going to end up getting like negative 6 plus 3. So the top is going to be a negative number. Looking at this factor here, I'll get something like -9 minus 2. That's also going to end up being a negative number. And then when I plug this in, -3.1, that's also going to be negative. So I know that I have a negative number divided by two negative numbers multiplied. This will be a negative number overall. So that's how I know that the graph is going down. It's going towards negative infinity at that point. On the flip side, on the other side of the, oops, I meant to get an eraser. On the other side of the asymptote at -2.9, again, plugging that into the factored version, I'll have, like, in the numerator, negative, it'll be about -6 plus 3. It's still going to be a negative number in the numerator. In the denominator, that will be a -6 minus x. That's also negative. But this factor here will end up being positive. So I have a negative divided by a negative times a positive. This will end up being a positive number overall. So I know that this part of the graph is moving towards positive infinity. You follow that strategy for both asymptotes, and you'll find out that this one is going up, this one is going down. And so then you're able to kind of put all the components together to get the structure of the graph. So again, it's looking at the behavior near the asymptotes to figure out what the overall graph looks like. All right, so I've got 3 more examples. I'm going to pause this video and then start a second video.